Well, good evening and welcome to Logos Research Associates live stream broadcast for March 2026. My name is Jay Siegert. I'm former president of Logos Research Associates, also current founder and director of the Starting Point Project. It's my own ministry, but we're glad that you're joining us for this presentation. I enjoy all of them, but this one in particular is of certain interest to me, so I'm looking forward to that. So I get to be the host this evening, which is a bonus for me as well. If you're not familiar with Logos Research Associates, let me get you up to speed. I'll read a little bit of our background. Logos Research Associates is a fellowship of scholars and scientists that are committed to upholding a high view of science and a high view of Scripture. We sincerely believe that scholarship, logic, and the scientific method can and should be used to show the Bible's historical claims are both credible and ultimately superior to the secular model of origins. Logo sponsors many creation research initiatives and projects involving many different experts in scientific disciplines, all working towards the goal of increasing the explanatory power of the biblical creation model and of origins and Earth history. The goal of our live stream broadcast is to provide you with the opportunity to hear from top researchers who will convey cutting edge scientific evidence for the Genesis creation account. Before we go any further, let me just open up in a word of prayer. Dear Heavenly Father, we just thank you so much for these times that you allow us to gather together. We thank you for all the people who have worked behind the scenes to put them together, and then also for all of our guests who bring the knowledge you have given them over the years, and not only knowledge, but wisdom as well. We are looking forward to this particular presentation, and we pray all these things in Jesus' name. Amen. So it's my pleasure to do an introduction for tonight's guest, which is Dr. Jason Lisle. I will read his background, and if there's any time left in the program, I'll let him speak. He's just got a great background. Dr. Jason Lisle is a Christian astrophysicist who researches issues pertaining to science and the Christian faith. A popular speaker and author, and a really good speaker, Dr. Lisle presents a rational defense of literal Genesis, showing how science confirms the history recorded in the Bible. Brought up in a Christian family at a young age, he received Christ as Lord. Since then, Lisle has always desired to serve the Lord out of love and gratitude for salvation and to spread the gospel message to all people. Dr. Lisle double majored in physics and astronomy with a minor in mathematics at Ohio Wesleyan University. He then went on to obtain a master's degree and PhD in astrophysics at the University of Colorado Boulder. Then he used the SOHO spacecraft to analyze the surface of the sun and made a number of interesting discoveries, including the detection of giant cell boundaries. Since then, Lisle has worked in full-time apologetics ministry. He wrote a number of planetarian guides for the Creation Museum, including the popular Created Cosmos. Dr. Lisle has authored a number of best-selling books on the topic of creation, including Taking Back Astronomy, Stargazer's Guide to the Night Sky, The Ultimate Proof of Creation, Discerning Truth, and Understanding Genesis. So with all of that, I get to turn it over to Dr. Lisle. Thanks for joining us.
Thank you. Thanks, Jay. Appreciate that. So our topic this evening is the James Webb Space Telescope and some of the discoveries that have been made using that spacecraft. And it's a remarkable instrument. And so I do want to spend some time actually talking about the spacecraft itself and how why it's so important, why it's such a good use of your 11 billion tax dollars, because it really is, and it's made some wonderful discoveries. And then we'll see how those discoveries are relevant to creation. And so I have some slides here that I can show you that'll hopefully help with this. So here is the spacecraft itself, the James Webb Space Telescope. So it looks like that. It's an interesting looking spacecraft. And I want to sort of explain this spacecraft by comparing it to its predecessor so that you can see the similarities and differences with the Hubble Space Telescope. And I do that because most people are at least somewhat familiar with the Hubble Space Telescope and the remarkable things that it's found. So here's Hubble. It looks like that. It's got a mirror that is 2.4 meters across. That's 7 foot 10 inches. So if I could put that mirror behind me, it would be taller than I am by quite a bit. And the bigger the mirror, the more light gathering power a telescope has. It can draw in more light more quickly and basically see fainter things. But the main advantage of the telescope, which by the way was launched in 1990, named after Edwin Hubble, who discovered the redshifts of galaxies, that they're proportional to the distance of galaxies. We'll talk about that later, how that implies that the universe is being stretched out or expanded as the Bible predicted. But the main advantage of the Hubble over ground-based telescopes, because there are ground-based telescopes that are much bigger than Hubble and have greater light gathering power. Again, 2.4 meters. That's big for a space telescope, but it's for a ground telescope, it's pretty small. The advantage of Hubble is it's in space. It's above the blurring effects of Earth's atmosphere. Light travels through space from, even the nearest stars trillions of miles away, the next star besides the sun, trillions of miles away, and that light travels in perfectly straight lines. There's a little bit of gravity, but perfect clarity for trillions of miles until it gets to the Earth's atmosphere. And in the last few miles, it gets blurred a little bit because the Earth's atmosphere has density differences. It's kind of like looking down the road on a hot summer day. You know how things look a little bit blurry there. A telescope amplifies that effect. So even when you're not looking down a road, even when you're looking up into space, you see that blurring effect. It's called seeing, and it's the bane of all astronomers. We hate seeing. We like the fact that we can breathe, so atmosphere's good, but it's very inconvenient for astronomy. The Hubble Space Telescope is above all that, and so it sees these images with crystal clear. These wonderful images we didn't have before Hubble. Before 1990, any image of a galaxy that you would see would be just a little bit blurry because it was taken with a ground-based telescope. And that ended in 1990, a little bit after 1990, because remember when they first launched the Hubble Space Telescope, it actually had a problem with the mirror. The mirror curvature was very slightly off, and they had to go up and fix that with CoStar. And the newer instruments have been designed around that problem. So it now has perfect clarity. They basically gave it glasses very shortly after it was launched. Now, Hubble sees basically what you see. It's sensitive to the same wavelength range that our eyes are sensitive to. It can go a little beyond human vision, a little bit into the infrared, a little bit into the ultraviolet, but more or less it sees what you see. And that's different with James Webb. But that's nice because it's kind of like what you would see if you were there. Now, that being the case, sometimes the images that we get from Hubble are what we call false color. And that's because Hubble actually has more filters, more color filters than the human eye has varieties of cones. We have 3 varieties of cones. That's why there are 3 primary colors for human beings with normal, healthy vision. Hubble has more than that. And so there's different ways you can assign the colors to different filters. And sometimes they'll assign false colors, not to be deceptive, but to do science. Each of these colors represents a certain wavelength range. And so, for example, the image that you're seeing here, it's part of the Eagle Nebula. And it's a particular part called the Pillars of Creation, because the secularists believe that stars are forming there. They're not, but that's what's often assumed. But in any case, I've seen this nebula with my telescope, and it is in fact red. So sometimes the colors are different from what you'd see, but sometimes they assign the same colors as to what you would see. And so this image of Saturn, pretty much what it would look like if you were there. And this is a Hubble image of Saturn. Pretty amazing. Before 1990, the only images we had of Saturn that were this clear were from the spacecraft that had actually gone past Saturn, the Voyager and Pioneer spacecrafts that had been there. But with Hubble, we don't have to go there. We can see it with this clarity, even though it's 1 billion miles away. Pretty amazing. Being above Earth's atmosphere, it gives us crisp, clear images, and it can zoom in quite a bit. Now, even ground-based telescopes can zoom in as much as you want, but the more you zoom in, the blurrier things get. And so there's a trade-off. There's a common marketing gimmick. Telescopes that you'll see at Walmart or something, it can zoom in 500 times. Newsflash, any telescope can zoom in any amount. But there's a practical limit because it gets blurrier the more you zoom in, and at some point it's just a blob. So the advantage of Hubble, crystal clear images of galaxies, like this wonderful image of the Whirlpool galaxy, that was not possible before Hubble, not in that clarity. Any older images of galaxies, a little bit blurry. Now, today we've developed some new technology called adaptive optics that allows us to shoot a laser beam out and create a virtual star and basically compensate for the blurring effect of Earth's atmosphere. Pretty neat. And so we can get ground-based images that are almost as good as Hubble, but not quite. It still has that advantage, being above Earth's atmosphere. Hubble is in what we call low Earth orbit. It orbits just a few hundred miles above Earth's surface, little higher than the astronauts in the International Space Station. The advantage of that is if there's a problem with Hubble, we can fix it, as has already happened. Hubble has 4 different instruments in it, and those have been swapped out over the years. I don't know if people realize that Hubble has been upgraded multiple times with new instruments. And so that's the advantage of a low Earth orbit satellite. And we'll see that's different from James Webb, which is not in low Earth orbit. Now, one of the things that we wanted to do with Hubble is to see farther into space than we had seen before, and to see distant galaxies. And in order to do that, well, we're in a galaxy. We have to look through ours to see others, and some of our own stars get in the way. So they selected an area of our galaxy that is relatively sparse. It's up near the Big Dipper, and there's very few stars there. And they pointed the Hubble telescope there and did a long time exposure to gather in the light from these faint galaxies. And the resulting image was spectacular. This is what we call the Hubble Deep Field. It is stunning. And every one of those little specks that you see there, even the ones that are in the farthest background, those are galaxies with millions to, in some cases, trillions of stars. So those aren't individual stars. They're galaxies, collections of hundreds of billions of stars. Really amazing. And one of the things that Edwin Hubble discovered is that the farther away a galaxy is, the more its light has been stretched for whatever reason. Most astronomers today interpret that as expansion of the universe. We'll see there's a little bit of debate about that, but it indicates that galaxies are moving away from each other and from us, that the universe is getting bigger. And so the farther away a galaxy is, the more its light has been stretched. The galaxies, the farthest galaxies in this image, have had their light stretched 6 times. That's a redshift of 6. And those are the farthest galaxies in this particular image. Now, in secular thinking, the farther out you look, it's like looking back in time, they say, because the light takes billions of years to get from there to here. Now, I've written articles showing that that doesn't have to be the case. The physics of Einstein actually allows the light to be here immediately, depending on what synchrony convention you use. And I'm not going to talk a whole lot about that. But the point is, in the secular view, as you look farther out, it's like looking back in time. You're seeing galaxies not as they are, but as they were allegedly billions of years ago. Now, at a redshift of 6, you're looking back in the secular view, you're looking back 12.8 billion years into a hypothetical past. And again, I disagree with that. But the point is, that's only 1 billion years after the Big Bang, allegedly. And so it was a little bit surprising that they saw these fully designed, fully formed galaxies at such tremendous distances. Because they were expecting, if you go out far enough, you ought to see baby galaxies. And if you go out even further, you ought to see no galaxies, because they hadn't formed yet. And so they thought, well, we need to go even deeper into space. And so they selected another region and did what we call the Hubble Ultra Deep Field. This is going even deeper into space to a redshift of 8.3, which corresponds, in secular thinking, to a time only 700 million years after the Big Bang. And there's still galaxies there. And they're fully formed, fully designed galaxies. Pretty amazing. Well, we obviously, this in secular thinking, we need to go even further into space if we want to see when galaxies first started to form, galaxies in the process of formation. And theoretically, at a certain distance, there shouldn't be any galaxies because they hadn't formed at that time. And again, I'm not endorsing that view. I'm just articulating it. But Hubble can only go so far into space. It can only see so far. Why? Because of these redshifts. The farther away a galaxy is, the more its light has been shifted to longer wavelengths. Now, at a certain distance, the redshift is so much, the light's been so stretched that the frequency, that the wavelength range falls outside of Hubble's ability to detect. It's so redshifted that Hubble can't see it. It essentially becomes invisible. So what we needed was another spacecraft that can see these longer wavelengths of light and therefore can detect galaxies at much greater distances than Hubble. Hubble basically has a maximum redshift of about 8.3. Galaxies beyond that, it can't really see them because their wavelengths have been stretched beyond the limit, the detection limit of the Hubble's instruments. So that was the purpose of the James Webb Space Telescope, launched in 2022. It was planned back in the 1980s. Even before Hubble had launched, they were already planning a successor. The good folks at NASA like to think ahead, and I appreciate that. And I remember discussing this instrument back when I was in grad school. I think it was in 1998. I had an instrumentation class, and one of the guys, the professor there, was part of the team that developed certain parts of this remarkable spacecraft. It was really amazing. And back then we were calling it the Next Generation Space Telescope. They gave it that name, the James Webb Space Telescope. That was named later in honor of James Webb, who was in charge of NASA from 1961 to 1968. He basically was responsible for a lot of the funding in the Apollo program. He petitioned the federal government for funding. So if you're happy that we landed on the moon, you can thank James Webb, along with a lot of other wonderful people that worked on that Apollo program. So in the year 2002, they named the spacecraft after James Webb. He passed away before that, of course, so he never got to see that. But a wonderful tribute for a very good man who did a lot of good work at NASA. Now, the James Webb, one difference between it and the Hubble is it's much bigger. Again, the Hubble mirror is 2.4 meters across. The James Webb is 6.5 meters across. That's over 21 feet across. It's big. And because it's that big, it will not fit in any rocket that we have. And so rather than making one big mirror, they decided to make 18 smaller mirrors that are hexagonal in shape and fit together a bit like a beehive. Pretty clever. And those outer layers can fold back so that they can fit inside the rocket. And then once the spacecraft gets out to its final position, there's programming on the spacecraft that causes those mirrors to all line up so that they're all pointed properly. Pretty brilliant design, I have to admit. The engineers that built this, the scientists that designed it, brilliant folks, brilliant people. So it has that enormous mirror, and that gives it much more light gathering power than Hubble. It can see fainter things, or alternatively, it can see something as faint as Hubble in much less time. It requires less time exposure. So that's a wonderful advantage, but it is much bigger than Hubble. The other thing that makes it different is, as I mentioned earlier, it can see different wavelengths than Hubble. Hubble sees kind of what you see. The visible light range, it can go a little into the ultraviolet, a little to the infrared. James Webb sees infrared. It can go up into, it can see a little bit of red. It can't see blue or green. It can see red, and then it goes into the infrared portion of the spectrum, as you can see on the chart there. Pretty far into the infrared, a range of 6,000 to 28,000 angstroms. So pretty amazing. And most of the other differences between James Webb and Hubble are due to the fact that it sees infrared, not visible light. For example, one difference is that beautiful gold plating. You might notice the mirror has a gold tint to it. That's because it's gold. It's the mirrors themselves are made of beryllium, but they're plated with gold. And the reason for that is gold is a very good reflector of infrared. So if you want to make a telescope, if you want to build a telescope to see what we see, you usually cover it. You usually put a filter, you put a thin covering of either aluminum or silver on it. Like most telescopes you'd get at a store, the mirror is actually made of glass, and it's got a thin layer of either silver or aluminum on it. Aluminum's cheaper, silver's better, and that's good for visible light, but gold is what you want to use for infrared, because gold reflects infrared better. And that layer of gold is only about 800 atoms thick, so it's a very, very thin layer of gold on beryllium plates. Why beryllium? Well, this instrument needs to work at very cold temperatures, and glass contracts when it gets cold, and that would be a bit of a problem in space. Beryllium will contract only to a certain point, and then it stops contracting. That's one of the interesting properties of beryllium. So they made the plates out of beryllium. And by the way, they designed them to be a little bit too big here on Earth so that when it's out in space and cools off, they will contract to the right size. Again, just some of the brilliant thinking that had to go into the design of this amazing spacecraft. It cannot operate at room temperature. Why? Because at room temperature, we are giving off loads of infrared. Maybe you've seen, those thermal goggles. Sometimes you'll see those in the movies. Well, those really exist. They allow you to take in infrared, and it turns it into visible light so you can see it. But James Webb is designed to see infrared. And so at room temperature, everything's glowing. It would see itself. It would see its own heat, its own infrared radiation that it emits to space. So the James Webb Space Telescope has to operate in an extremely cold temperature in order for it to work properly, in order for it to see these wavelengths of infrared. And in fact, it needs to work at a temperature below 40 kelvins, 40 degrees above absolute zero. That corresponds to a temperature of negative 370 degrees Fahrenheit. Very chilly. And the problem is you put that out in space and you say, well, it ought to cool off. Space pretty cold. It is, but we got this big light and heat source nearby called the sun. And that's a problem. So what they did was they built this heat shield. That's that silvery thing that you see on the bottom of the spacecraft there. That sun shield is always between the mirror and the sun. So the spacecraft has sort of limited ways that it can point because that sun shield has to be between it and the sun. And that causes it to naturally cool off. It prevents the sun from heating the spacecraft. And so it just cools off. Once you launch it into space, it'll cool off naturally to a fairly cold temperature. By the way, that sun shield is about the size of a tennis court, just to remind you how big this spacecraft is. And it has multiple layers, and each layer cools it a little further than the previous layer. Again, a brilliant design. And then the James Webb Space Telescope, it has 4 detectors on it, 4 different instruments, each of which can detect a certain frequency range in the infrared. And 3 of those operate pretty well at 40 kelvins. But the 4th one, MIRI, operates far enough into the infrared that it needs to be cooled even more in order for it to operate properly. And so there's actually a cryo-cooling system on board that gets it even colder than it would be just from passive radiating heat into space. And that onboard instrument reduces the temperature to around 7 kelvins, 7 degrees above absolute zero, or negative 447 degrees Fahrenheit. Now, in order to get that temperature, it cannot orbit around the Earth because the Earth radiates heat into space. Now, Hubble doesn't care because it's looking at visible wavelengths, but James Webb cannot exist in Earth orbit. And so instead, we put it at what's called the L2 Lagrangian point. There was a French mathematician, Lagrange, who figured out 5 locations where you could put an object and have it orbit at the same speed as the Earth around the sun, where it would be in equilibrium there. It would continue to orbit at that speed. And we put the James Webb at the L2 Lagrangian point, which is about 1 million miles farther away into space, in the opposite direction of the sun, away from the Earth. And that allows the spacecraft to cool to the temperature that it should. The disadvantage, human beings can't travel that far into space. The farthest we've gone is the moon, which is a 250,000 miles away. The James Webb Space Telescope, it's 1 million miles away, which means if something goes wrong, we can't fix it. At least we can't send astronauts to fix it. If it's a computer problem, we might be able to update the software or something. But if something breaks on James Webb, well, that's $11 billion down the drain. But fortunately, it's been working very well so far. And so that's a wonderful thing. And also because it's inaccessible, it can't be upgraded either. That's another disadvantage that the Hubble didn't have. The Hubble's upgradable. The James Webb Space Telescope is not. Well, there were some predictions that the secular astronomers made regarding what this spacecraft would discover. Because remember, it can look out deeper into space, farther into space, much farther than Hubble, because it can see these longer wavelengths of light that the farthest galaxies should have. Since they're redshifted, the farther away, the more redshifted their light. And so secular astronomers predicted that you should see fewer and fewer galaxies as you go out deeper into space. Why? Because in their view, you're looking back in time, and eventually you ought to look back to a time where there were no galaxies. It's supposed to take several 100 million years for the first galaxies to form. And so if you look back to a redshift of 14, where the light's been stretched 14 times, you really shouldn't see any galaxies, because in their view, that corresponds to a time of only 300 million years after the Big Bang. And that's too short a time for galaxies to form. So you shouldn't see any beyond that distance. And you should see very few when you get closer to that distance, because only a few galaxies had formed after that time. Now, again, I reject that way of thinking. I believe we're seeing the universe in real time if we use the Bible standard of synchrony conventions, but that's another talk. This is their prediction. Furthermore, they were expecting that the farthest galaxies they would see would be basically baby galaxies, because galaxies are supposed to form as stars accumulate and gather together. And so the earliest galaxies should be very low mass, very few stars, and they should be clumpy and irregular because it's supposed to take time for galaxies to grow as they collide with other galaxies and become these beautiful spiral structures that we see nearby, spiral and elliptical galaxies. They were expecting that the farthest galaxies should be irregulars, clumpy, irregular, and very low mass because they're babies, right? And then finally, they were also predicting that these farthest galaxies would not have heavy elements. Now, in astronomy, a heavy element is anything other than the first few elements on the periodic table, really the first two, hydrogen and helium. Everything else is what astronomers call a metal, even if it's not a metal by a chemistry sense. So astronomers refer to oxygen and nitrogen as metals, even though chemists don't. We have our own terminology for that, these heavy elements. Now, why would the farthest galaxies not have them? Well, according to the Big Bang theory, the Big Bang is supposed to produce, the universe starts from a point, it's very hot, it expands, and from that initial energy, matter forms, but the conditions are right only to form the very lightest elements, hydrogen and helium, just a little bit of lithium and maybe a little bit of beryllium, but that's it. Boron, carbon, nitrogen, oxygen, the next elements should not form in the Big Bang because the conditions aren't right, according to the Big Bang theorists themselves. And yet the universe does have these heavy elements, so where did they come from? Well, secular astronomers believe that all the heavier elements were produced in the cores of massive stars when they explode. Now, most stars don't produce the heavier elements, but theoretically, the really big ones can in their core. And then when they supernova, when they explode, they've produced these heavier elements, oxygen, iron, and so on. And then they release that into the universe. And then the next generation of stars that accumulates from those elements, it has a small fraction of these heavy elements. And so the reason that all stars in the local universe have a little bit of carbon, oxygen, nitrogen, not a lot, but some, the secularists would say it's because they're contaminated from previous generations of stars that produced them. But the first generation of stars, having formed only from the gas produced in the Big Bang, should not have these heavy elements. And so these hypothetical metal-free stars would be called population 3 stars. We haven't observed population 3 stars. They're theoretical, but they were expected to exist in the farthest galaxies. So these are the secular predictions. And I thought, I better get on the ball and make some predictions myself because I don't believe in the Big Bang. I believe in biblical creation. And so I made some very different predictions about what the James Webb Space Telescope would find. And I basically predicted the exact opposite. So my first prediction was that we would find lots of galaxies, even beyond a redshift of 14, because I don't believe we're looking back in time. I believe we're seeing the universe in real time based on the way the Bible defines time. And again, that's another topic. That's another talk. But I don't see any reason why God would stop making galaxies at a redshift of 14 because I don't think you're looking back in time. So I think they're going to keep going all the way out as far as the James Webb Space Telescope can detect. Furthermore, I would expect these farthest galaxies would be fully formed, massive and well-structured, because I don't believe in baby galaxies. When God spoke the stars into existence on day 4, he spoke them into existence on day 4. They didn't need to grow from babies. Adam and Eve did not grow from babies. God created them as adults, and so I figure he made the galaxies as adults too. Now, I have to give a little bit of explanation for this. Galaxies come in a variety of sizes and masses. There are galaxies nearby that are relatively small, and then there are galaxies that are great big. My prediction is that the distant universe would also reflect basically that range. You'll find some small galaxies, but you'll also find some great big ones, because I believe they were all spoken into existence by God, and that they did not grow from stars as they accumulated and so on and over billions of years, because I don't believe in billions of years. Finally, I predicted that these farthest galaxies will have heavy elements, because I don't believe in the Big Bang, that there was a bang that just produced the 4 lightest elements and none of the heavier ones. I believe in special creation, and I know from the Bible that the heavy elements existed already on day 1, like oxygen. Oxygen is what astronomers would call a heavy element, and I know it existed on day 1 because Earth's made on day 1, and according to Genesis 1 verse 2, the Holy Spirit was hovering over the face of the waters. Water is H2O, O is oxygen. So I know that on day 1, oxygen already existed. I know from Scripture stars are made on day 4, so the heavy elements already existed before the stars did, and that's the opposite of what the Big Bang theorists believe. So I'm predicting those farthest galaxies will have heavy elements. They will not have the metal-free population 3 stars. And I got to tell you guys, I'm confident in the Bible. I really am. And I was so confident that these secular predictions would be wrong. I wasn't sure that mine would be right, but I was sure that the secular ones would be wrong because they're based on the Big Bang. That I also predicted how the secularists would respond when their predictions failed. And so basically, I'm predicting that they're going to see lots of galaxies even beyond a redshift of 14, and they're going to see fully formed galaxies at those distances and heavy elements. And rather than give up the Big Bang, which predicts the opposite, they'll simply push galaxy evolution back to an earlier time. They'll say, I guess we haven't gone far enough into space. So basically, I predicted that secularists will respond to their failed predictions with statements like this. Webb discovers that galaxies formed much earlier than previously thought. They're just going to push, rather than give up the Big Bang, they'll try to adjust galaxy evolution scenarios so that they can happen much more quickly to produce these galaxies so that we're already seeing them even at a time of what in their view is less than 300 million years after the Big Bang. Okay. So, and I made these predictions back, you can read them on our website, the Biblical Science Institute, biblicalscienceinstitute.com. And I made those predictions in January of 2022. This was before the James Webb Space Telescope had given us any data. I'm not even sure it had reached its Lagrangian point yet. We didn't get data from the spacecraft until July of that year. So again, these are predictions made well in advance because that's the hallmark of good science, is the ability to make successful predictions. So July of 2022, we get the first images back of the farthest regions of space. Do we see regions that are almost empty because the galaxies hadn't formed yet? Well, here's what we see. Here's what we saw. Galaxies upon galaxies upon galaxies. Every one of those little fuzzy clouds that you see there is a galaxy with hundreds of billions of stars in some cases. Pretty amazing. And if you're wondering, well, what are the redshifts? They go all the way out to and beyond a redshift of 14. Yes, we did find galaxies beyond a redshift of 14. So what are the results of the James Webb Space Telescope data? Lots of galaxies at great distances, even beyond a redshift of 14. There's some studies that go out to 16, 17. There's at least one study I've seen that goes out that detects a galaxy at redshift 20. Amazing. That's way beyond what the secularists were predicting. Now, they'll have to verify these spectroscopically. There's a couple different ways to determine redshifts. And there's like a quick and dirty way, and then there's a more precise way. So they'll have to verify these with the more precise measurement. But we have verified galaxies, even using the more precise method, at a redshift beyond a redshift of 14. Pretty amazing. And lots of them, by the way. And these farthest galaxies, are they babies? No, they're fully formed, massive and well-structured. There are galaxies at these incredible redshifts that are comparable in mass to nearby galaxies, like our own Milky Way. Amazing. Not surprising from a creationist perspective. Very surprising from a secular perspective. What about heavy elements? Did they find these population 3 stars that lack heavy elements? No, the farthest galaxies do have detectable heavy elements in them. James Webb Space Telescope is equipped with a spectroscope. That's an instrument that can divide light into its various wavelengths, and that will tell you, based on what wavelengths are missing, what the element is that made the light. And we've detected things like oxygen, carbon, I think, in these most distant galaxies. So the creationists' predictions were right on. The secular predictions were way off. What about my prediction about how they would respond? Remember, I'm claiming that rather than give up the Big Bang, they'll push galaxy formation back earlier. And they'll say things like, Webb discovers that galaxies formed much earlier than previously thought. How did they respond? Here's an actual quote. Galaxies started forming much earlier than many astronomers previously thought. That's from Yukon Today, August 9, 2022. Here's another one. Massive galaxies formed earlier in the universe than previously known. That's Nature News, July 27, 2022. Here's another one. Evidence is building that the first galaxies formed earlier than expected. Sky and Telescope, January 10, 2023. Here's another one. A lot of galaxies could have been formed in the universe much earlier than previously thought. That's space.com, January 12, 2023. So, pretty neat. And the reason I was able to do that, the reason I was able to make any of those predictions is because the Bible's true. I was able to make the 3 predictions about what James Webb would detect based on the information the Bible gives me in Genesis. And I was able to predict how people would respond based on what the Bible tells me about human nature. It tells me that people don't want to bow the knee to the biblical God. And the Big Bang gives them an intellectual cushion to be able to think that they can do that they can explain this universe apart from the biblical God. So if you've been keeping track, Again, the secularists predicted fewer galaxies at great distances and basically none beyond a redshift of 14. That's false. We found some studies indicate thousands of times more galaxies than the secularists were expecting at that distance or at those given distances. The creation predictions that there would be many galaxies at great distances, even exceeding redshift of 14, that's been verified by the James Webb Space Telescope. The secular prediction was that the farthest galaxies would be low mass and clumpy baby galaxies. That turned out not to be the case. The creation prediction is that God made the galaxies mature as he made Adam and Eve mature, and that's what we're seeing. The farthest galaxies are fully designed and mature. There's even evidence of barred spirals, and those were in secular thinking, those were supposed to take like 6 billion years to form, where they have like a straight bar and then it goes into a spiral. And those have been detected at much greater distances than secularists were expecting. And then the secularists predicted that the farthest galaxies would have only population 3 stars. That's not the case. They do have heavy elements, as we creationists predicted. So on all counts, our predictions were certainly better than the secularists. And I think that's pretty exciting. It's not surprising, but it's pretty exciting. So that's pretty neat. And then I want to show you some other information too that I think you'll find very interesting. I need to switch over my my slides here. Let's take just a second. Because there were some other things that I think surprised everybody. And creationists weren't necessarily predicting this, but neither were the secularists. And so let's talk about some of these things. This is very, very new, so take it with a grain of salt. But I was looking at some of the data that was produced by this remarkable instrument and some of the technical papers that other fine astronomers had done on the appearance and sizes of these galaxies as they appear. And I discovered something really interesting. And I wrote a technical paper on this. It's called Sizes of Galaxies in James Webb Space Telescope Data Suggest New Cosmology. I published this in the Answers Research Journal. I think it was published last year, 2025. I discovered this previous, but it takes a little while to get it written up and peer reviewed and everything. And basically, the sizes of these galaxies are not what you'd expect if the standard idea of how the universe expands is correct. And let me show you how this works. Normally, when you look at something, the farther away it is, the smaller it looks. That's pretty obvious. A car that's right next to you looks pretty big. If you see a car driving, several miles away or up on a distant mountain, it looks tiny. That's angular size. Angular size is how big of an angle something covers in terms of my perception. And generally, galaxies that are nearby look pretty big. They have large angular size. And then the farther away they get, they look smaller. That's just perspective. Okay, that's pretty easy to understand. And so if I could move a galaxy, if I could take a galaxy of a given size and move it twice as far away, it would look half as big in each dimension, and so on. And that's true if space is not expanding. But back in the 1920s, the late 1920s, when Edwin Hubble discovered that all the galaxies were moving away, several scientists used Einstein's theory of relativity, which was relatively new at the time, and said one explanation for that, for the fact that galaxies are moving away from each other, is that the fabric of space is being stretched out and the galaxies just kind of go along for the ride. That's a pretty neat idea. And until recently, I thought that was the right idea. Now, the Big Bang is based on that, but that the fabric of space expanding does not require a Big Bang. It's compatible with it maybe, but it doesn't require it. And so I always thought that there was a creation-based cosmology in which the fabric of space is expanding. If that's the case, then this law of perspective stops working at a certain distance. You see, if light is moving through space that's being stretched out, it turns out it acts like a kind of magnifying glass and causes distant galaxies to appear bigger than they would otherwise. And so what would happen is if the fabric of space is being expanded, then it's like what you see on the bottom diagram there. Galaxies that are nearby should look big. As they get farther away, they should look smaller and smaller until you get to a redshift of 1.6, and then they should start to look bigger again because of this magnifying effect. So even though they're further away, they'll look physically bigger. And I remember studying this in grad school and doing the math to show that works. And by the way, if you're wondering, how does that work in detail. I'm not going to go through the math, but you can check out any cosmology book. It's something that is well established in the math. If the fabric of space expands and light is moving through expanding space, distant objects will appear bigger than they should otherwise. And given the standard parameters of the universe, the rate at which it's expanding and so on, the magnification will overcome perspective at a redshift of 1.6. Galaxies will start to look bigger again. So that's not what we see, though. I was expecting, when we got these James Webb deep fields back, to see distant galaxies that are larger than galaxies that are closer. And that's not what we see. The galaxies seem to get smaller and smaller, as if the fabric of space is not expanding. Interesting. And so again, the Hubble law is simply the observation that galaxies, the farther away they are, the more redshifted they are. Apparently, galaxies are moving away from each other and from us. The standard explanation that was proposed by 4 scientists is that this is due to the expansion of space. The fabric of space expands and the galaxies just kind of go along for the ride, as you can see. But I thought, what would happen if the galaxies are just moving through space, but the fabric of space is not expanding? Would that explain the fact that they continue to look smaller the farther out you go? See, the standard model invokes what's called the Friedmann-Lemaître-Robertson-Walker metric, after the 4 scientists who discovered this, sometimes shortened to just the last 2, the Robertson-Walker metric. That is the mathematical description of space that expands with time, and the galaxies just kind of go along for the ride. But what if space is not expanding, and the galaxies are just moving through it, and the farther away they are, the faster they are? Then the redshifts would just be caused by the Doppler effect. And so I'm calling this the Doppler model. And so I did some calculations. How big would a galaxy, take a typical galaxy nearby and move it out to different distances, how big would it look? And it turns out, if the standard model is true, if the Friedmann-Lemaître-Robertson-Walker metric is true, that's the red line. The red line indicates how big a typical galaxy should look, how big its angular diameter would be as a function of redshift. Redshift is the number along the bottom there. And once you get out to, so they look smaller until you get to 1.6, and then they start to look bigger again if the fabric of space is expanding. That's the red curve. If the fabric of space is not expanding and the galaxies are simply moving through it, and the redshift is due to a Doppler effect, that's the yellow curve. That's how big galaxies should look. You can see they just continue to get smaller and smaller and smaller. They never get bigger again. And just for the sake of completeness, I also included a third model that's not very popular called the tired light model. This was proposed back in the 30s by Fritz Zwicky. He said that the universe is not expanding and the galaxies aren't moving, but the reason we have redshifts is because light just loses energy over time for whatever reason. I'm not sure he ever had a real compelling reason for that. Most people don't accept the tired light model, but it does predict that galaxies would continue to look smaller with distance. Okay, so those are the 3 predictions. Red, if the standard model is right, if the fabric of space is expanding. Yellow, if my new Doppler model is right. And green, if the tired light model is right. And so then I took the actual sizes of measured galaxies in the published literature. I'm not measuring these myself. I'm using other astronomers who know what they're doing. And these are their results. The white points are from Hubble observations, because Hubble can do nearby galaxies. And then the colored marks are from various other studies. And I've put the name of the study up by the mark there. And you can see that indeed the galaxies continue to get smaller, and they track pretty well with the yellow line. Now there's quite a bit of scatter. And so I thought, what if I take those galaxies in a given redshift bin and average them together? What would the average size look like? It's this. So those yellow points are the average size of a typical galaxy at different distances. And you can see the data match almost perfectly with the Doppler model. And so when I saw that plot, I thought, oh, I'm onto something here. This is very exciting, because this means the idea that the fabric of space is expanding according to this Friedmann-Lemaître-Robertson-Walker metric is probably wrong. It could mean that the fabric of space is sort of static and the galaxies are just moving through it. There's other possibilities as well, but that's pretty neat. And in addition to predicting the size of galaxies, I can also predict their luminosity. I'll do this one just real quick. It's a little hard to see, I know, but basically, if this is the computed absolute magnitude, the true brightness of a galaxy, red line if the standard model is right and fabric of space is expanding, and the black line is if the Doppler model is right, and the blue line is the best fit to the data. And you can see the best fit to the data pretty closely matches the Doppler model. So that's pretty exciting. So what does this mean? The angular sizes, how big they look, of distant galaxies are consistent with their redshifts being caused entirely by the Doppler effect. They're just moving through space and not the Robertson-Walker metric, the expansion of space. The brightness of distant galaxies is likewise consistent with the Doppler model and not the Robertson-Walker metric. And so I think that's pretty exciting. Now, there are ways to get around this. You could, let me back up. You could say, well, because I've assumed, I've taken a galaxy of a given size and pushed it out to different distances. That's how I get the 3 lines. But you could argue, well, but galaxies, a long time ago were much smaller and they've grown. And so the reason the data matches the yellow line, it's just an astonishing coincidence that the fabric of space is expanding, but galaxies were actually that much smaller, and the two effects exactly compensate. And I had a critic argue that, actually. Yeah, but that prediction does not match with the luminosity data. So I don't think that's the right answer. But this suggests, first of all, that there is no substantial galaxy evolution. The galaxies that we see at tremendous distances are about the same as nearby galaxies. We already know their mass is comparable because their luminosity is comparable to nearby galaxies. But secularists believe that these galaxies are much denser than nearby galaxies and have somehow expanded for reasons that we don't know. But we already know that the structure, mass, and metallicity of distant galaxies is similar. It may not identical, but it's similar to nearby galaxies. And so this new model explains why. It's because God made all the galaxies pretty much similar to where they are nearby. It's just that we had been misestimating their angular size because we used the wrong metric. And so the neat thing about this model, if it's true, if I'm right about this, then the Big Bang cannot occur, because the Big Bang requires an expanding fabric of space. If galaxies are just moving through a non-expanding space, then you run the movie backwards. They don't go back to a point. They'd all miss each other because they have sideways motion as well. They don't go back to it. There'd be no Big Bang. And so what I'm suggesting is that these new James Webb Space Telescope data apparently disallow a Big Bang if my interpretation is right. And I'll grant it doesn't have to be. There are other explanations for this. But this is devastating evidence to the Big Bang. And it's also consistent with the ASK model, which is my answer to how do you get the distant starlight from those galaxies to Earth in the biblical timescale. And I'm not going to go into detail on that. You can ask about that during the Q&A if you're interested in that. But the bottom line is this is exciting new research. It's something that nobody was expecting, and it paves the way for further biblical cosmology models. We might now turn our attention to what would be a general relativistic solution. In other words, the physics of Einstein. What would be the proper metric that describes the way the universe actually is? Because we've been assuming the Friedmann-Lemaitre-Robertson-Walker metric for the last 100 years. And these new data suggest that metric is wrong. So it's very exciting time to be a biblical creationist. We've already seen that it's the biblical creation model that has made the successful predictions about what James Webb has detected so far. This new model, the Doppler model, predicts that we'll find galaxies at greater distances and that they'll have a specific size. You can read that in the article. So this model makes quantitative predictions about what James Webb will detect in the future. So that's very exciting, because in the next few years, we might find either a refutation of the Doppler model or confirmation of it. And so it's a very exciting time because we can now see deeper into space, where we can test different models that make different predictions. Nearby, the models all make the same predictions, but in distant space, they make different predictions. And so we can start doing some really good research along the lines of cosmology. And I dare say that it's the creation models that are now in the lead, because we're the ones that have made the best successful predictions recently. And I think that's very, very exciting. So I think I will conclude with that. Do check us out on the website as well, biblicalscienceinstitute.com, where you can read about this. I have a layman's summary of this stuff on the website, or you can go to the technical article on the Answers Research Journal. And Yeah, I think we'll stop there with the presentation, and happy to go to Q&A.
Oh, thanks, Dr. Lisle. I know you were just scratching the surface. I'd want you to keep going and going. I have a lot of questions myself, but this should be have deference towards those who are listening. So we will have questions up on the screen. We'll go through those, and if I have enough guts, I'll interrupt with some of my own questions. But as soon as we have the first one up on the screen, I'll read it off. But I guess while we're waiting for it to be posted, you would probably agree they will never, ever find evidence that disproves the Big Bang, because they will just retrofit the Big Bang to fit with what they're seeing. And then they'll often brag about how the evidence fits their theory.
Yes, the Big Bang isn't so much a theory as a philosophy through which the evidence is interpreted. And so no matter what new evidence comes in, that's how I made the prediction that I made about how they'd respond. I knew they wouldn't give up the Big Bang. I thought, well, they'll change their models of galaxy evolution, which is exactly what they're doing.
Sure. Here's our first question. Can you explain in simple terms, example, high school physics, undergrad physics, how these galaxies, allegedly billions of light years away, can still be interpreted as being only thousands of years old?
Well, yeah, just because something's far away doesn't make it old. Maybe you're referring to the starlight issue. How did we get the light here in a short period of time? And I've written articles on that. My answer is what I call the ASC model, ASC. And what that does is it uses a little known principle of the physics of Einstein, that the speed of light can actually be different in different directions. And that's called a synchrony convention. Basically, the speed of light in one direction is not a property of nature. It's something that we humans get to stipulate, and that tells us how to synchronize clocks, or how to define what constitutes synchronized clocks. So the bottom line is the light can actually get here immediately if you're using the right synchrony convention. And I've suggested that the Bible uses a visual synchrony convention because everybody did but before the 1600s, everybody used a visual synchrony convention, effectively stipulating that incoming light is instantaneous. What surprises people is that the physics of Einstein allows for that. And Einstein even wrote about it, that the speed of light in any one direction it's not a hypothesis, it's a stipulation, which I can make of my own free will in order to arrive at a definition of simultaneity. Now, based on that short elevator pitch, I wouldn't expect you to understand it or believe it even, but check out my articles on that topic, the anisotropic synchrony convention and the model thereof. I've got a technical article on the Answers Research Journal back from 2010, and then I've got a number of articles on the Biblical Science Institute website that cover that topic.
Great question. Next one. Oh, same one. Halton Arp, formerly of Caltech, and intrinsic redshift.
Halton Arp, he was a neat guy, and he challenged the secular model in a number of ways, and I think that's a good thing to do. That's how science progresses, is by challenging the existing paradigm. He argued for some unusual interpretations of redshift. I don't think he's right about that. It was a neat thing to try. One thing he would argue, that distant quasars are connected to nearby galaxies, that they must actually be at the same distance because it looks like they're connected, or they're in a close proximity, even though one has a great redshift and the other has a relatively low redshift. And so he was arguing the redshift must be intrinsic somehow. It's possible. I don't think it's the best explanation, to be honest. He would argue that the probability of this quasar being next to that galaxy is like 1 in 1,000, which it is, but the number of galaxies you have to search through to find one of those is about 1,000. So it's actually consistent with it being a chance alignment. So I don't think he's right about that, but I'm glad he challenged the paradigm, because that needs to be done.
Good question. Next one. Would a very large galaxy be surrounded by more empty space because they pulled in matter via gravitational accretion of matter? They are big because they're swept up by surrounding matter.
Yeah, I think that's true. Of course, they'll attract other galaxies too, but we find that galaxies occur in sort of, it's kind of like a cobweb. If you were to see the distribution of galaxies, there are big sections of space that's relatively empty. And of course, I would argue, well, God probably created it that way. I don't think they've moved very much in 6,000 years, but nonetheless, you do find, we find strings and voids. That's kind of how galaxies are organized. And the Sloan Digital Sky Survey, I've worked a little bit with the data from that. It confirms that there are sections of space that are relatively empty, but I think that's part of God's design. But it would be compatible with either model. Let's put it that way.
Great answer. And another question. With universal expansion causing galaxies to look larger, isn't that also supposed to make the light more diffuse too? So redshift and not image diffusion would indicate right model.
So Rich, yeah, it doesn't make, it makes the light, it would make it fainter. Yes. It doesn't make it blurrier or anything like that. Now, the tired light model did predict that distant galaxies should be slightly blurry, and that's been refuted. These galaxies are crystal clear. So that's one of the reasons the tired light model is not well favored today. Does it make them? Yeah, it does have an effect on the apparent brightness of the galaxies. And the last graph I showed that was, I didn't flip it for PowerPoint, so it's color on white, which made it hard to see on PowerPoint. But that one shows that the luminosities of these galaxies are more consistent with the Doppler model than the expansion of space model. But the predictions aren't as different as they are with the angular size. The beautiful thing about the angular size is the predictions are very different. By the time you get out to a redshift of like 13 or 14, there's like a 5 times difference in the apparent angular size of a galaxy, where there's only a 50% difference in luminosity. So it's not quite as extreme, but it does make a difference. Yes.
I'll interject one really quick. A number of years ago, it was kind of a popular idea to talk about, the decreasing speed of light, which maybe is somewhat related to tired light on Barry Setterfield, Australia. Mm-hmm. Wrote about that. It was very popular for a while. It's pretty much disappeared. Would you be able to summarize, like, what was the problem they were making? Was it just a crude measurements that they were doing a long time ago that didn't give them the precision that they needed?
Yeah, that's the main thing. And again, I'm glad he tried that. I'm glad that he proposed that, because a lot of times secularists will assume that something's constant and it isn't. Something doesn't change over time when it does. And so I'm glad he tried that. I think that was a neat thing to try, but the data don't bear it out. He was looking at some of the older data where they simply weren't very precise in some of these older charts. And I think there's really good evidence against that, directly against it. There's physical reasons to think that the round trip speed of light is constant, because the round trip speed of light is related to the relationship between energy and mass. And if that changes, then the relationship between energy and mass must change. And that causes some big problems. Also, we see light echoes in distant regions of the universe, like the supernova that happened in one of the Magellanic Clouds. Some of the light from that reflected off of material that was some distance away and then headed toward Earth. And that allows us to measure not the one-way speed of light, but it allows us to measure the round-trip speed of light way over there at a time that should be long ago, if you believe that we're seeing into the past, and yet it's exactly the same as the speed of light nearby. And so that suggests that the round-trip speed of light has not changed. The one-way speed of light, it's not that it changes. It's just that it's not a property of nature. It's something we get to stipulate, and we can stipulate it to be instantaneous as long as the return trip speed is half c. The round trip speed is set by God, has to be c in vacuum, and there's good evidence that it doesn't change and that it can't change in vacuum.
Okay, next question. If galaxies are going for the ride, then they're increasing their gravitational potential?
Yeah, that's an interesting question. I'm not sure, because if the universe is infinite, then their gravitational potential doesn't change. I don't know for sure the answer to that. It depends on the structure of the universe. There's all kinds of questions about where does the energy go, where does the energy from the light goes that gets redshifted and so on. And so there's questions about that. Maybe it goes into the potential energy of the galaxies. Perhaps is the answer.
I guess another quick related question with secular astronomers and physicists believe that the universe is made up 95% of dark energy and dark matter, which is interesting. But and it seems like there's been arguments both ways for dark matter that, who knows, maybe it's out there. You can comment on that. The dark energy seems to be something they were winging it because they are thinking the universe is not only expanding, but it's actually accelerating. So they need energy. So enter dark energy. Maybe you want to comment on that briefly,
Sure.
Because a lot of people don't know anything about it. And then there are different creationists who actually say different things that are kind of contradictory. So it'd be nice to have some clarity on that.
Gotcha. I think there's good evidence for dark matter. Dark matter is anything that we can't see, but we have good evidence that it exists because it pulls gravitationally on something that we can see. And there's very good evidence that there's a lot of dark matter out there. What is it? We don't know. The most likely candidate is some kind of particles that we haven't detected, that because they don't interact with ordinary matter frequently or very strongly. So weakly interactive massive particles is the most likely candidate for dark matter. I think that's good. There's good evidence for that. And there's several different lines of evidence that converge and give us the same numbers for the amount of dark matter. For example, the speed at which stars orbit the galaxy tells us about the mass interior to that orbit. And so we know the rate at which stars are orbiting. We can measure their Doppler shifts. We can get that speed very precisely, very accurately. And that we can compute the amount of mass interior to that orbit, wherever that orbit is. And that allows us to map out the mass of a galaxy. And it's about 10 times bigger. The mass is about 10 times larger. That can be accounted for by simply dust, gas, stars, stuff that we can see. Also, gravitational lensing. When light from distant galaxies passes by nearby galaxies, it gets bent. And the amount of bending tells us the amount of mass that's in that galaxy, that we can compute that. And it gives the same number. And so those are two independent lines of evidence that dark matter really exists. The only alternative to it would be that the law of gravity is slightly wrong. And that law has been very successful in predicting the motion of planets and things like that. We can pin down, even the precession of Mercury. I'm not just talking about Newton's law of gravity, but the Einstein equivalent of it, the Einstein version, which predicts the precession of Mercury very precisely. So that makes me think that dark matter's the more likely candidate. It's not absolutely proven, but I think it's far more likely than modified physics. There are some creationists who disbelieve in dark matter. Most of them are not astronomers, to be honest with you. I think creation astronomers, we are almost in complete agreement that dark matter is the most likely candidate for explaining why we see these observations that we see. Dark energy is more tentative. This new model that I've proposed, the Doppler model, eliminates the need for dark energy. It explains the luminosity and angular sizes of these galaxies without any need for dark energy. Now, I said it eliminates the need for dark energy. It doesn't disprove dark energy. Those are two different things. Dark energy could still exist, but we don't need it to explain why galaxies look the way they look in the Doppler model. We do need it in the Friedmann-Lemaitre-Robertson-Walker metric, because you need it to explain the acceleration of this expansion, but you don't need it if the Doppler model's right. So it'll be interesting to see if the Doppler model turns out to be right. And again, it's very new. So I proposed this just a year ago. So don't take it as biblical truth. Take it as something that's compatible with biblical truth and might be right, but might be wrong. But True. If it turns out to be right, it eliminates the need for dark energy.
Okay, great. Let me see. If both large and small galaxies are in the same region, heterogeneous mixing, isn't that a problem for Big Bang cosmology?
I don't think it is. They've done computer simulations, and you can get galaxies of different sizes depending on the starting conditions. So I wouldn't use that as an argument against the Big Bang.
Okay. Is there a discernible structure to the galaxies around the Milky Way, or is there any structure to galaxies in the universe that we can see?
Discernible structure to the galaxies around the Milky Way. In terms of their internal structure, galaxies are almost always either spirals or ellipticals. A very small fraction of them are what we call irregular galaxies, very small fraction. There's only, like in the Northern Hemisphere, there's only one that I know how to find in my backyard telescope. There's more than that, but if you want to see it in your backyard telescope, I only know of one irregular galaxy, and it's probably a spiral that's actually been distorted a little bit. If you're talking about how the galaxies themselves are organized, they tend to be organized into strings and voids. They come in clusters, and sometimes clusters of clusters. Some of them are massive, like the Virgo supercluster, which contains over 2,000 galaxies. And you can see that in a small telescope. You can see several of them in a small telescope, some of the brighter ones. It's in the constellation Virgo, and it's a good spring object to look at. If you want to do a Messier marathon, you can get a lot of them right there in the Virgo cluster. And sometimes you'll point it there and you'll see several galaxies in your field of view of the small telescope. It's wonderful. So they're organized into structures, clusters, and then larger clusters. And on the largest scale, strings with sort of holes in between them, a little bit like Swiss cheese.
Cool. All right. Next question. Hey, John. What are some of the funniest storytelling you have heard as excuses for seeing large mature galaxies where they were not expected?
Well, there are only two that I've heard at all, and the big one is galaxies must have formed much quicker than we thought, much earlier. But there are physical limits to that. And I saw a paper a couple years ago, back when the first James Webb images came out, and he said this is the limit of the maximum size that you can get of a galaxy, given the Big Bang, given the baryonic interactions and so on, because there's only so many atoms available. And I haven't checked to see whether they've now discovered ones bigger than that, whether it violates that limit. I need to follow up on that. So that's very interesting. So that's the main reaction, is that our models of galaxy evolution need refinement. They obviously aren't exactly right. They need to be refined. We need to get galaxies to form much earlier. The only alternative I've seen is one apparently secular astronomer, somebody who doesn't accept biblical creation anyway, proposed a combination of expanding universe and tired light. I think they tried to combine the two. And what that would effectively do is double the age of the universe. So so instead of 14 billion years, it'll be 28 billion years old. And that means that gives the galaxies a little bit more time to evolve. So that's the only alternative. They still haven't given up the Big Bang, but they've modified it. They've said basically half of the redshift is due to expansion and half is due to tired light. And that doubles the age of the universe. I did see a technical paper. It got published. So apparently the secularists are okay, at least considering that as a possibility.
Interesting. What are some of the criticisms you had to deal with involving the James Webb Telescope predictions that you made?
Some of the criticisms, I haven't really heard any. Most people have been very quiet about this. I think there's, not a lot of, they don't want to announce from the rooftops that a creationist predicted these things. And so they're a little reluctant to refute me. I haven't seen any. Now, there might be some, don't get me wrong, but I haven't seen any in the literature that says, hey, here's why Lyle's prediction, obviously my predictions were right, but here's why he shouldn't be given credit for those. Here's why the secular model is still better than the creation one. I haven't really seen that. Now with the Doppler model, I did get a response to that. Luke Barnes did a very gracious paper saying here's why I think Lyle's wrong about this, and I've responded to that. And you can read those in the Answers Research Journal. I think Luke was wrong about that, and I pointed out why. But his tone was nice, so I appreciate the cordial interaction, even though he's taking a pro Big Bang stand. It was a very cordial dialogue that we had.
That's always encouraging to hear. Question 1, what is the highest form of life you think exists out in space? And 2, do you recommend grad students not use their last name if they're working on a doctorate or master's?
Okay, so I don't think that there's life out in space other than the astronauts who are currently on the space station. And hey, maybe in a month or so, we'll have astronauts orbiting the moon. That'll be pretty neat, because it's been a while since that happened. But other than human beings, I don't think you're going to find life out in space. Some people have said, what about angels? I'm not sure angels are classified as living. The Hebrew word nefesh chai, living creatures. The Bible says the life's in the blood. Angels don't have blood because they're non-physical. I don't know. I guess you could, maybe you can count angels, but other than that, I don't believe that we're going to find I don't believe we're going to find biological life out in space. I have some theological reasons for that. There are some astronomical reasons for that too, some physics reasons for that. God formed the earth to be inhabited. That's Isaiah 45:18. And granted, that doesn't prove he didn't other places, but I think that's the implication of the passage, is that earth is designed for life, and the rest of the universe is designed to give God glory and to be a clock for us, to be for signs, seasons, days, and years. So I don't expect to find life out in space. We have the unique honor of being made in God's image. And does that make us the highest form of life? Well, how do you evaluate high versus low? We're not the biggest creature. We might be the most intelligent, maybe, but we're certainly the only creatures that are made in God's image. That's a unique honor. With regard to grad students using their last name, you have to use your last name in the classroom. It's just, if you want to write an article on creation, you use a pseudonym. And that's perfectly acceptable. People say that's dishonest. It's not. Mark Twain is a pseudonym. I mean, it's common for writers to use a pseudonym, a pen name. That's perfectly fine. If you wanted to write a creationist article, something defending creation, then you should use a pen name. But you use your given name when you get your when you do your actual classwork, of course.
All right, another question: are all nebulae and gas clouds the remnants of supernova explosions, and is it proof of decay, not birthplaces?
So relatively few nebulae are supernova remnants. Some of them are. The Crab Nebula is a supernova remnant. There's a few others, but a lot of nebulae are massive. They're too big to be a supernova remnant. There's too much mass in them. The Rosette Nebula, for example, the Horsehead Nebula, the Great Orion Nebula, that's not a supernova remnant. There's some places where God just put a lot of gas out in space, and if there are stars nearby, they'll make it glow, and you get these lovely colors. And so, are nebulae proof of decay? No. The supernova remnants, I suppose, but and I don't think there's any evidence that they're birthplaces of new stars. The secularists believe that because we find stars that can't last billions of years, like blue stars. Blue stars cannot last billions of years. Nobody would disagree with that. They use up their fuel too quickly. And so the secular idea is they must be forming, or they must have formed recently in a nebula, because it's the only way they can think to do it. The idea is the gas collapses, but we don't see that happening. We don't see anywhere in the universe where gas is collapsing in on itself. Normally gas expands. Normally the conditions in a nebula are such that the gas pressure is much greater than the meager inward force of gravity. Now, once you have a star, because it's compact and because gravity is inversely proportional to distance, the gravity will keep the gas together. But to make a star, I'm not convinced that the conditions ever occur in space to where you can get the gas cold enough that it'll just collapse in on itself. I won't never say never, right? I'm not being dogmatic on it, but I'm very skeptical that stars can form naturally.
Real quick, regarding the star formation, how serious are secular scientists about the idea that, well, one star explodes and that force pushes gases together? It doesn't seem like the physics would work with that at all, but do they still propose something like that?
They still do. That's still a good way to try to get the gas to compress in on itself. Russ Humphreys and I one time did a quick back of the envelope calculation, and we figured it would take about 4 stars to explode relatively simultaneously in a similar region for the gas pressure to be sufficiently overcome by the pressure waves. So we think that's pretty unlikely to happen. But yes, that is still proposed as one mechanism of star formation. Of course, they can't use that mechanism for the first stars.
Right.
So, it's still a bit of a problem.
Sure. Okay. Another question: when God said, "Let there be light," He had infinity to deal with. How far would the light have gone?
Well, the light goes forever until it hits something, normally. So it would continue to go into space. Yeah, we don't know exactly what that first light was. Apparently, it was such that the Earth had day and night for the first 3 days, and then God replaced that temporary light, whatever it was, with the sun on day 4. I've toyed with the idea of different ideas for what that light could have been. Is it something that on day 4 got stretched into the cosmic microwave background? I don't know. I mean, there's some neat ideas about that. We don't really know what it was, but it would have gone infinitely until it hits something.
All right. This may be off topic, but I wonder why we are not able to get clearer pictures of 3i Atlas with Hubble or James Webb.
I don't know offhand. I thought they had pointed the James Webb Space Telescope at it. They also got some images from the Mars rovers, but I don't think it was that spectacular of a comet. It wasn't very bright. It wasn't very bright for a comet. The neat thing about it is it's interstellar. I wanted to go look at it, but I didn't really get a clear night, and then it moved into the morning sky, and I'm not getting up early to see a comet. So I'm not sure why they didn't get better images. It might just be it's a fairly faint comet and not a particularly spectacular one.
And have you heard of a young Earth creationist that claim that relativity allows for the distance between galaxies billions of light years away that are much closer according to relativity?
I have not heard that, other than, of course, from the light's point of view. From the light's point of view, the galaxy's distances shrink to 0. But in terms of our point of view, no. I mean, there is such a thing as length contraction. And so as you move close to the speed of light, distances compress in the direction of motion and only in that direction. And theoretically, if you were to reach the speed of light, the universe would compress and become two-dimensional in terms of its, well, actually two-dimensional because there would be no time. And so every trip would be instantaneous because the distance goes to zero. From light's point of view, the distance is zero. But from our point of view, it's not. So I don't think that relativity makes the distances shorter in a way that would answer the light travel time problem in a way that most people would find desirable.
Okay. Do you think there are issues with the digital signal processing methods used to filter out heat noise to produce the cosmic microwave background?
Oh, that's an interesting question. With the digital signal processing methods, I've heard that claim. I don't know. I don't know if it's true. I know that we've had several different ways of measuring the cosmic microwave background. It's definitely there. There's definitely a cosmic microwave background. Whether the maps we get, how accurate the maps we get of it are, I don't know. I've always assumed they're pretty accurate, but I haven't studied the processing methods well enough to give you a good answer on that. It's a good question.
Do we believe in a finite number of stars that were created, and because of the curse, we see breakdown and degeneration? Example, SNR.
Yeah, that's a good question. Do we believe in a finite number of stars? Nobody other than God knows the answer to that. Some people have argued that, yes, there are a finite number of stars because God calls them all by their names. God has a name for each star. Yeah. But could God give an infinite number of names to an infinite number of stars? Yeah, God could do that. So I'm not sure that's the best argument. There's Olber's paradox, but that might be resolved by the fact that the farther away they are, the more redshifted they are. That might even account for the cosmic microwave background. So we don't know if there's a finite number of stars or infinite. We don't know that. Nobody knows but God. And with the curse, we don't know how the curse affected space. We know how it affected the Earth a little bit because we're given specific examples: thorns and thistles, death, disease, obviously, because the world was very good before the curse entered it. We don't know how the curse affected space. Are supernova a result of the curse? We don't really know that because it doesn't. A supernova, a star exploding, is pretty neat, and it gives us some information on distances to galaxies and things like that. I've seen some supernova in other galaxies, and they're fun to look at. It doesn't pose a problem for the Earth as long as the sun doesn't supernova, which even according to the secularists, it won't do that. So I don't think that the curse. We know the curse affects human life in a negative way, but as to how it affected the universe, we really don't know. We don't have much information on that. I would be hesitant to say that things like supernova are a result of the curse. I suppose they could be, but I wouldn't make that claim.
I'll throw in one of mine really quick too. I know according to the biblical model, it doesn't necessitate the Earth, the solar system, our galaxy being in any particular location in the universe. However, if the Big Bang is true, there really shouldn't be any special places. Is there any current credible evidence that our solar system / galaxy is somewhere towards the center of the universe?
That's a good question. There's no data either way. There's no data one way or the other. We could be in a special location, but there's nothing I've seen that would require that.
So we don't have, I know years ago they talked about quantized redshifts. Has that kind of gone by the wayside?
I looked into that in some detail, and it's interesting. Based on my analysis, the quantization we see, it's rather meager, and it's fairly consistent with what you would see in a random distribution. If you just have a random distribution of galaxies, they will tend to cluster, and you'll get these meager quantized redshifts. So I don't think that it indicates that our solar system is in a special location. I actually published an article on that a while back, so you might look at that. But
Sure.
Even in that article, I didn't know what to make of it. I just determined that the quantized redshifts are not a result of processing artifacts. They're real. They're in the actual data, but they're rather meager, and so I'm not convinced that they indicate that our solar system or our galaxy is in a special location.
Okay, thanks. What about plasma cosmology? You don't need dark matter if the main force of the galaxy at the galaxy level is electromagnetic instead of gravitational.
So yeah, I don't think that's a good way to go. I've looked into that a little bit. Danny Faulkner has studied this more than I have, and he agrees with me. But you might look at some of his writings on plasma cosmology, because he's done more on that than I have. The bad news for plasma cosmology is the electromagnetic force is so strong, and because there are equal number of positive and negative forces in the universe, that almost any system is very close to neutral electrically. And so over large distances, gravity wins, even though it's much weaker at like a nuclear level than the electromagnetic forces by many orders of magnitude. On the large scale, it dominates because there's no anti-mass. Mass only adds, whereas electromagnetic forces cancel very, very well over large distances. So the universe is not, on the cosmic scale, the universe is not driven primarily by electromagnetic forces. There might be a very small effect, but it's not much. It's primarily driven by gravity.
Okay, next, do stars have musical type waves affecting life?
Well, not affecting life, afraid not. Stars do give off vibrations. They pulsate, and you can turn that into sound. And I've heard this, and it's interesting. I've heard the sun. The sun sounds almost like static, but it does have that 5-minute oscillation. It's weird. It's not pleasant. So people, there's music of the spheres. It's unpleasant. It's not something you'd want to turn on as a noise machine before you go to bed. Some of them are very interesting. I've heard certain stars, because of the way they rotate, they make these very interesting sound patterns. Not really musical, but interesting, but very interesting. And because sound can't travel through the vacuum of space, it affects our life in no way whatsoever.
Okay, I know you have dismissed time dilation models in the past by those from John Hartnett, Russ Humphreys. Could you explain a little bit more why?
Yeah, so in the Humphreys, in his original model, and by the way, he's abandoned it as well, and so has John Hartnett. John Hartnett is now endorsing my model, the anisotropic synchrony convention. He likes that, but it was a neat idea. It would require that the number of galaxies is finite, and that they stop at a certain point, and that our galaxy is very close to the center of that gravitational mass. That could be the case. We don't know that it's the case, but the reason that I ended up rejecting it is because I did the math. And when you do the math, the time dilation is tiny. It's very, very small. It's like 2% between here and the farthest galaxies. And so and you say, well, it would have been greater in the past, but that means the expansion rate of the universe, if it's only 2% difference, then the expansion rate of the universe is off from the secular amount by only 2%. And so the universe wasn't much smaller 6,000 years ago. So the bottom line is, it doesn't generate enough of an effect to get light here within the biblical time scale. It might reduce light travel time by like 2%. So yeah, you're down from 10 billion years to 9.8 billion years. Yay, that's in the right direction, but it's not enough to get it here in 6,000 years. It was a quantitative issue. Qualitatively, it's a neat idea, but quantitatively, the math just didn't work out.
Sure. Oh, appreciate the commentary. I think this is the last question we're going to do then. If most astrophysicists believe dark matter does exist, even creationists, why haven't we properly detected it yet? Or have we? Seems like experiments keep finding none.
Okay, well, in a sense, we have detected it. We've detected it by the motions of stars around their galaxies. That indicates that it's there. Maybe what you mean is we haven't detected it in a laboratory. We don't know what it's made of, and that's true. We don't. The leading theory is the reason we can't detect it in a laboratory is because the particles that consist of dark matter do not interact with ordinary matter very strongly. They don't interact by electromagnetic forces or the nuclear strong and weak force. And is it like neutrinos? Neutrinos are really hard to detect, even though there's trillions of them going through you every second. There's trillions of neutrinos going from you. They're produced in the core of the sun. They don't interact with ordinary matter very much. They only interact gravitationally. And so if the particles that make up dark matter are like that, and sterile neutrinos are one candidate, I'm not sure if that works. But in any case, if they're like that, if they don't interact with ordinary matter, it'd be very difficult to detect them. If the only way they interact with ordinary matter is through gravity, then the only way we can see dark matter is the way we do see it, namely it affects the motions of stars and their galaxies and the way light bends when it goes around the galaxy. So in a sense, we have detected it. We just can't produce it in a laboratory because we don't know what it is. We don't know what kind of particle it is.
Sure. Interesting thought. I'm going to add something to that, and then we will wind down, and you can give me your feedback on this. We didn't, there's so much we could cover that we don't have time to. But when you talk about the Big Bang, if you push the secular scientists far enough, well, what was this singularity? Well, fluctuation in the quantum vacuum. Okay, well, where'd the quantum vacuum come from? You keep pushing them. Eventually, they have to say, well, we believe that at some point it came from nothing. So because they got nothing else, there can't be something, or otherwise, where did that something come from? So they will typically talk about something coming from nothing, and tying this in really quickly. Sometimes they'll say, we've actually shown in the laboratory where these virtual particles can come in and out of existence. We got a vacuum set up, there's nothing there, and the particles come in and out of existence. Yeah, it's really brief, but we've seen that happen. And just one of my comments is always, wait a minute, you're saying that a huge chunk of the universe is dark matter, which is something you can't detect. How do you know that in your vacuum you don't have dark matter that's producing some of these particles?
Well, that's an interesting point. That's a good possibility. But even so, even if we don't have dark matter there, we do have space there. And most people think of space as nothing, but it's not. Space is something. God had to create empty space, believe it or not, because space is not nothing, because space has properties. For example, it's three-dimensional. Ever thought about that? Space has three dimensions. You can pass three lines at right angles through a point, and that's it in space, because space is three-dimensional. It's something that God created. It's not nothing. It's something. The fact that it's not made of atoms doesn't mean it doesn't exist. It just doesn't have, it's just not material, but it does exist. And so when these virtual particles come into existence, they come into existence from space, and then they usually go back into space. They can be transmitted over distances. They have an infinitesimal amount of energy that they borrow from space, and then they return to space. So they're not coming from nothing. They're not coming from nothing. They're coming from the vacuum. And when physicists talk about vacuum, we don't mean the absence of everything. We mean the absence of matter, but not the absence of everything. There's still something there, because it has dimensionality. I can measure it. Space has length, height, width. So it's not nothing. And with regard to the Big Bang, some of them would say, yeah, it comes from nothing. Some of them would say it comes from a quantum fluctuation, but that requires vacuum. And so some of them will say, well, there must be another universe, and ours popped into existence from that other universe. That's actually becoming kind of popular. But it kind of pushes the question back, where did this other universe come from? And some would say, well, maybe the other universe is eternal. Even though our universe isn't eternal, maybe this other universe from which it sprang is eternal. And then that gets you around a question of a first cause. Because I would agree that if something is eternal, it doesn't require a cause. God is eternal, doesn't require a cause. I get that. But it just pushes the problem back, really, because the universe has properties, it's material, it's particulate. God isn't like that. God is what we call, he's simple in the sense of he's not made up of parts, whereas the universe is. It's different parts, it's different components, and so on. So the Big Bang has a lot of problems, and the singularity is just one of them.
Sure. Well, we really appreciate you spending this time enlightening us on an awful lot of stuff. And again, you were just getting started and warmed up. So
My
there's a lot
pleasure.
more things I think we could cover in the future. So what we want to do just at this point is just remind people to check out logosresearchassociates.org, the website. Lots of great information there. Consider supporting one of the great research projects that they currently have going on. Subscribe to the Logos Research Associates newsletter. And if you do that, you'll get a free copy of Creation Evolution Headlines, produced by David Coppedge. Is just great resource. And then this is obviously live, but this recording will soon be available on the website. You can pass on to other people if they didn't get a chance to watch it live. And then an announcement about our next presentation. That's going to be Wednesday, April 8th at 9 p.m. Eastern, like we usually do. Dr. Randall Price, PhD in Middle Eastern Studies, Master's of Theology in Old Testament and Semitic Languages. And the topic is Digging for Truth, Archaeology and the Confirmation of Biblical Historicity. That's going to be a great topic. So we're looking forward to that. But just once again, thanks, Dr. Lisle, for taking this time to be here with us. I've heard you give many talks, and there are a lot of great creationists out there. There's a smaller handful that are not only really good with the topic and the material, but are really good at conveying it so that everyone else can understand. And so you're one of my favorites, and I appreciate everything that you bring to the creationist community.
Thank you. Appreciate that.
Sure. All right. Well, I will close in another word prayer, and then we will look forward to seeing you next time. Dear Heavenly Father, we just thank you again for these times that you allow us to gather, and just always such great information. Again, not with the point of winning an argument, because we know we're not dealing with an academic debate. We're dealing with a spiritual heart issue. Help us to all understand that. Help us to be strengthened in our faith, more confident in our faith, to again more boldly and graciously share the gospel message with those around us. And we just thank you again for this time and pray all these things in Jesus' name. Amen.